Okay, it is my pleasure to welcome you to this tutorial session on encrypted control. We start with a small delay due to the previous session, but I think we will pick that up quickly. So this tutorial aims for familiarizing you with this fairly young field of encrypted control, and we try to bridge like the pioneering realizations to modern implementations and using code to really give you the opportunity to use this hands-on. And there is a link to our GitHub repo where you find our MATLAB code, which should help you to follow what we discuss in this tutorial and maybe reproduce it back home. Okay, this tutorial is, it has three parts. The first part will be given by myself, and it's an introduction to encrypted control, and we will discuss one pioneering realization using a simple crypto system, and then we move on to parts 2 and 3, given by Junzo and Niels, and they will deal with more complex crypto systems, allowing to implement more powerful control schemes. In the first part, as I said, introduction is the keyword here, so we really want to open the door to this field, which might be new to some of you, and then introduce like the first realization, which was only 9 years away. So the first paper on encrypted control was end of 2015, so I think it's fair to say it's a really, really young field, and hence I'm happy that you all showed up here so that we can distribute it a bit more. In the second part, the LWE-based crypto systems will be at the heart. The LWE crypto systems, it's a special kind of crypto systems which feel very different to what you might know about crypto systems. So the Payet crypto system, which I will be introducing, that starts, as you might expect, pick two large prime numbers, do something with them, and the LWE schemes, they feel very, very different, and you will learn about them in the second part, based on the GSW scheme. And then in the last part, we kind of pick up the state-of-the-art crypto system CKKS, and Niels will introduce something about that for you. Okay, let's start with my part. That is the introduction to encrypted control. First of all, I should motivate what it is about and why should we care about it. Well, as we all know, control systems become more and more connected. And when I say this, I'm thinking about cloud-driven control. I'm thinking about network multi-agent control, wireless sensors and actuators. And yeah, you can think about these two illustrations there, cloud-driven transportation as well as smart grids. And I mean, I can also abstract that a little bit, and we will use that abstractions here throughout the tutorial. On the left-hand side, we see here a simple cloud-based realization of a standard control loop. That is, everything is as you will know it, only that we will evaluate the controller in a cloud for whatever reason, outsourcing it due to performance issues or whatsoever. On the other side, you see multi-agent systems, and in research, there's a lot going on in the literature. You find many works also dealing with the multi-agent scheme. Since the cloud-based view is much more easier to pick up what encrypted control is about, we will focus on the cloud-based realizations in the following. Now, what is the similarity between both of these expressions? Well, we have communication of sensitive data in both cases. So we assume that the states, the input, the controller parameters, that is all sensitive data, and we might not want to share this to another entity. And we have external processing of this sensitive data. So evaluating a controller is evaluating an algorithm. I do something with my data, and that happens at the external entity. And that is an issue if we believe that, that the cloud, for instance, is curious about the data we are evaluating there. And hence, we might have confidentiality, privacy issues, but also integrity and availability might be on risk, and that brings me to this standard CIA triangle that we often find in IT security. And right, you might think that security for control systems, that sounds a bit artificial. Why should I care about this? Why is this different to standard IT security problems? Well, it's a real-world danger, and there are many malwares explicitly acting against cyber-physical systems, and here is just a bunch of them. And you will definitely have heard about Stuxnet, but there are other malware attacking like either integrity or confidentiality or the availability of our process data. And we are today dealing with the confidentiality part. So we are aiming for privacy. Well, more precisely, we are aiming for privacy of system states, of controller parameters, of computed inputs, despite an honest but curious agent, meaning we assume that this cloud here will be honest, so whatever we upload, it will process it and evaluate algorithms, but it will be interested in the data. That is the curious part of it. And hence, taking this into account, it becomes clear that kind of a standard encryption of the communication is not sufficient. And that is good for us because it gives us some works, because this encrypted channels, that is standard, right? So you could use standard tools to realize this, and that wouldn't be a challenge for us. But then if the cloud, as in this picture here, gets access to the decrypted data, then we have the issue that if it is curious, it will have access to all the data, and that should not be the case. Now, how can encrypted control avoid this situation? Well, in a picture, that's quite easy to illustrate what we are aiming for. That is, we simply forget about the decryption in the cloud. That is, we have here our system, we measure the states with a sensor. At the sensor, we encrypt the data, we send it to the cloud where the controller is evaluated, and we never decrypt it again. So the controller is evaluated on this encrypted data. It produces an encrypted input, and then this input is decrypted only at the actuator and applied to the system. And hopefully that is a nice looking picture or setup for you, but clearly the question is, how can I realize this? Or can I realize this at all? The answer, I mean, based on the title of this session, clearly that is no surprise. The answer is yes, we can do something as here with the encrypted control loop. However, we need to learn how we can do it. And how we can do it? Well, there are some key technologies that might be of interest there. Clearly, what we need to be able to do is computations on encrypted data. That is really the heart of what we are doing here. And therefore, we need here, or we use here, homomorphic encryption. That are special types of crypto systems which allow you to do some operations in an encrypted fashion on data. And typically, this set of operations is quite limited and mainly involves encrypted additions and encrypted multiplications. And in fact, I can specify this. So we call a crypto system additively homomorphic if it comes with an operation O+ here. And this operation O+ is such that if you want to evaluate the sum of two numbers, but you only have access to encrypted version of these numbers, then you can apply this O+ operation on this ciphertext. It will reduce and result in another ciphertext. And if you then decrypt the resulting ciphertext, then you in fact gain what you were looking for, that is the sum of your numbers. Meaning, using this operation O+, the cloud is in the situation that it can add numbers, right? And that might be of an help to realize this goal we have of an encrypted control scheme. On the other hand side, we call a crypto system multiplicative homomorph if it offers the operation O times. That is same story as before. We have two encrypted values. If we use this operation and decrypt the result, then we will obtain the multiplication we were looking for. And in the end, that's it. So we are kind of limited to these two operations, and that might sound a bit bizarre. That sounds like elementary school, but afterwards there came many other operations we learned about. But please take into account that if we think about these operations on a binary level, that is true, false, 0, 1, then the addition is nothing else than an XOR, and the multiplication is nothing else than an AND. And these two gates, to be precise, combined with a 1 signal, they are functionally complete. Meaning, with these two gates and the 1, you can construct every algorithm you want to implement. And hence, once these two operations are given, we call a crypto system fully homomorphic because it gives you all the abilities to implement stuff. Now, the issue here is, why is there encrypted control? Why is there encrypted machine learning? If we think about the circuits based on these two gates, then the result would be highly inefficient. So the goal here is to kind of get a feeling of how to reformulate controllers such that they can be implemented in an efficient fashion. That's kind of the goal. Fully homomorphic will be the topic in the parts 2 and 3. And here I will speak about an additively homomorphic scheme to give you this first realization of an encrypted controller. That's the idea. Okay, and this crypto system will be the Payet crypto system, and I will briefly introduce this crypto system. It is a public key scheme, and I will give some comments in this direction in a second. For the moment, this slide, it's not important for you to follow it line by line. It should just give you an idea of how crypto systems are, for example, constructed. And the Payet crypto system is kind of, as I also said, a classical crypto system, which starts with this sentence, pick two large prime numbers that you might find in many crypto systems as well. And with these two large prime numbers, you construct two things. One is the public key, and the other one is the secret key. What is the difference of these keys here? The public key can be freely distributed without any issue. So you can distribute it to the world. And this is exactly the concept which is used, for instance, if someone wants to send you an encrypted email, but you haven't exchanged a key before. Then this guy can simply use your public key, send you an encrypted email, and only you with the secret key can decrypt the message, right? That is the idea of a public key scheme. And here with these homomorphic schemes, they are often public key schemes, and the idea is that everyone can encrypt data, everyone can also use the homomorphisms, but then only the entity having the secret key can decrypt the result. That is kind of the idea here. Now, since many schemes start like this, they clearly build on number theory. For instance, you might say, how can it be that the public key is simply the multiplication of these two primes, and then the secret key makes use of these two primes as well? Why can I not simply evaluate a prime number decomposition and construct or reconstruct the secret key? Well, for small numbers, this works, but for large numbers, it's known that prime number decomposition is hard, at least on classical machines. With quantum computers, there exist different algorithms. Luckily, the schemes you will learn about in part 2 and 3, they are quantum secure, so that is not an issue. Here with the Payet scheme, yeah, quantum computers might be able to break it. But if you haven't this, then picking two very large prime numbers, it's a hard life for you to do the prime number decomposition, and therefore you can't reconstruct the secret key. And here's a funny quote by Hardy, a very famous mathematician from Cambridge, who said in 1940 that he believes that number theory, it will take many years until it finds its ways into applications. Clearly, he was proved wrong very quickly. Second World War, Enigma, Turing, decrypting it or breaking it, and then afterwards, like all the modern cryptography kind of builds on number theory, right? So that is no surprise that we find it here. Okay, let's complete the scheme. So it allows you to encrypt plain text, and that is important from an integer set, from a bounded integer set, where kind of the size of this set is determined by the size of the public key. And then it takes also a random number. Also, this is important because these public key schemes, they're usually constructed in a way that if you take two equal messages, you will get mostly two different ciphertexts. So it's not that you have this pair as with symmetric encryption schemes, that there is for every message you have one ciphertext. That's not the case here. Same messages can lead to different ciphertext. And that also means that the ciphertext space is much larger. And then here we have the decryption routine. And don't worry why it works. That is number theory. And of course, the scheme is constructed in a way that it is reversible. So pick a number, encrypt it, decrypt it, you get the same number again, of course. Well, this slide is a standard crypto system, but what is new now is that you have this encrypted operations available. And I claimed that this scheme is additively homomorphic, hence there should be an encrypted edition. And in order to kind of construct this, think about how the encryption of the sum of two numbers would look like. And then you will find out that you kind of find the multiplications of the two routines for the individual numbers in the result. And that is, in fact, the way how this O plus operation is realized here. So it's not general, it's specific to the scheme. Here, the encrypted addition refers to a multiplication of the ciphertext. And that's it in the end. So we have now our O plus operation. However, with only additions, it might seem very hard to encrypt controllers, and that is indeed the case. However, if we add one ingredient, and that is the Payet scheme also has another partial homomorphism, which is it allows you to evaluate partially encrypted multiplications, meaning you have one plain text factor, you have one encrypted factor, and then there is an operation O dot, which allows you to evaluate this partially encrypted multiplication in an encrypted fashion, leading to a result as the ciphertext, which, if you decrypt it, results in the multiplication. Why do we have this additional homomorphism? Well, that is, something which most additively homomorphic schemes offer you, because remember that we are dealing with integers here, meaning the multiplication of two integers we can also phrase as the addition, right? We can z1 times add the numbers z2, which is then the same. And for this addition, we can use our additive homomorphism. Luckily here, we do not have to do this because, well, if you multiply and multiply the ciphertext, then this is nothing else than taking the original ciphertext to the power of z1, and this is then a realization of this O dot operation for this specific scheme. And then one comment, well, these schemes should be secure. Typically, this classical crypto systems, they all build on the hardness of a certain problem, which is here related to this prime number decomposition. More precisely, it is the one phrased here. But this is in brackets because this is not important for us, because we take these schemes off the shelf. It's the cryptopher's job to make sure that they are secure, and we are only using it. We are not developing our own schemes and hence our own crypto system, and hence we do not have to worry about security. This is in other hands. Okay, so that's it. We have our first crypto system which has this homomorphisms, which we can then use to realize an encrypted controller. And I will now show you the one pioneering realization, which was kind of the starting point of encrypted control. Yeah, and this is quite simple linear state feedback. Because if you think about linear state feedback in this cloud-based implementation, for whatever reason, the motivation for doing so not so strong, right? Why should I put a linear state feedback controller in the cloud? But this may be useful in this multi-agent setup, right? So always think about that what we discuss here might also be applicable in the multi-agent setup, and there it can make sense to have like a linear controllers acting together on different machines. But let's stick here with the cloud-based realization. The setup is that we believe that the states, or that we design it that way, that the states and the inputs should be secure. For the moment, it's okay for us that the control parameters are plain text values. And in this setup, if we want to evaluate this thing then in encrypted fashion, well, the homomorphisms we just introduced, they obviously allow to do so, right? So we have this partially encrypted multiplications here with the plain text controller coefficient and the encrypted states. We get a ciphertext as a result. This ciphertext can be added up using the operation O+, and then we have an encrypted input value. And that's it for the moment. And this scheme, as I said, or a very similar scheme, was introduced end of 2015 by Kogisu, and that was kind of the starting point. Well, is it really that simple? So is it really that once we have these homomorphisms, we can just apply it the way as here on the slide and we are ready? No, of course not. Because what is ignored here in this prototypic realization is that we are dealing with integer data, right? So, or we have to deal with integer data because our crypto systems are designed such that they need integer messages. Here we have kind of real-valued states, real-valued controller parameters, and as a consequence also real-valued inputs. And hence we need to map our data to the set of integers, to a bounded set of integers, and then we can apply the encryption. Okay, how do we do that? How can we map our data to this bounded set of integers? And after doing that, also recover it, right? So in the end, we are interested in our more or less real-valued u. So fair if we only get approximations, but still, at the end, we are looking for the u and not for an integer-based variant, right? So how can we map our data and then also be able to recover it? Well, we want to map it to this bounded set of integers, which we will refer to as ZQ here. For the Payet scheme, the Q is nothing else than the public key, right? So you can simply equal that. And mapping our real value data to this bounded set, we will do so within 2 steps. First, we will map our data to the set of integers, unbounded, and then we will map the integers to this bounded set of integers, ZQ. Obviously, the second step is quite easy, and you can realize it with a modulo operation, because the modulo operation kind of leads to this sawtooth, always mapping to this bounded set of integers here, right? And luckily, thinking about recovering, we can also have this partial inverses. We will use this one. Clearly, you could also use a different window, but you can have an inverse for a window of length q, so to say, right? If you stay in that window, then all is good, and you can go back and forth. And we will use this window between minus q half and plus q half, which allows us to preserve signs of x and k, for instance. And then the inverse is given by this operation, but that it exists is the important thing and not how it looks like. Okay, so we now mapped our data to ZQ. That was the second step. From that, we need to solve the first step, so mapping our data to the set of integers. Well, that is also quite simple, and we use simply a scaling and rounding operation, similar to fixed point operation. That right? It's very related here to fixed point operations. Many things that pop up. So what we will simply do is we scale our axis or the controller parameters by a factor s, typically large. Think about it as 100 here. Then this kind of preserves 2 decimals of your values. Right, and then once we scaled it and rounded it, we have an integer, we apply the modulo q operation, and we are in the set we need to encrypt the data. And later on, we can go back to the decrypted value, and then we need to be able to recover it. We apply this inverse modulo operation, and then we need to rescale it by simply dividing by the scaling factor. And then we obviously have an approximation of our original data, and that's it. So going back to our linear state feedback, we simply need this integer-based reformulation here, and using the scaling and rounding operation, we end up with these integers. We use the modulo operation on all the operations here, but it's sufficient to have it like at the end. And then later on, we use this inverse modulo operation to go back to the original data, and then we consider rescaling. And my question to you for the moment, think about it for a second, is what should the rescaling factor look like, and which value should be within these 2 bounds such that the partial inverse works? So what is the interesting value here? Well, hopefully you came to the conclusion that we need to rescale by s square. Why s square? Because, I mean, we kind of accumulated scaling factors here due to this multiplication, right? And we have to keep this in mind. We have to have this bookkeeping in the background, similar to fixed point arithmetic, where the same happens as well. And then only the final result needs to stay within these bounds. It doesn't matter, like, I mean, one element here could be negative and the other one positive. And one could be so large that it breaks out. It doesn't matter. If the sum is within the bounds, all is good, and we can apply our partial inverse there. Okay, because that is very important that we stay in these bounds, because otherwise we run into an overflow, right? We leave the domain where everything works nicely, and that is an issue, as you might know. So here is the Ariane 5 rocket, which exploded without any people on board in 96 due to an overflow issue, right? So there was only a tiny issue in the program that led to this catastrophe here and loss of billions of dollars. So we kind of have the same issue here. Also, encrypted control is not yet applied on spacecraft, but it is kind of even more difficult here, as in encrypted computation, we cannot check whether overflow happens. We cannot detect it, right? And that is an issue, and that is also one of the design challenges. We need to make sure that an overflow never happens because we won't recognize it. We just would have this catastrophic result at the end of the control loop, but we have no chance to detect it in the meantime. Okay, so keep that in mind. And now we are ready to point out the code which we use for implementing it, right? So the whole session is called a code-driven tutorial. So far, I talked about why we should care about encrypted control. I talked about a simple crypto system which allows you to do encrypted computations. We talked on the paper or on the slides about a pioneering realization, but now we also want to have it in code, and therefore, again, the QR link to our GitHub repository with MATLAB code. Why MATLAB? We use MATLAB because we believe that in the field MATLAB is still the software many people use, and that was the reason, right? So we will learn that in order to use MATLAB for this encrypted computations, we need to tweak it a bit, and it is not super efficient to do it there, right? There are much more efficient realizations based on C++ or Python or whatever, but in order to kind of pick you up with the software you are using, we thought that MATLAB is nice, and also you can simply look in every function and learn how it's realized. And it's really to get these insights and not to end up with an efficient product. So please do not apply our toolbox and have it somewhere in the field. There use more professional realizations, just to give you a feeling of how it works. Okay, so what do we need to do in order to implement it using our toolbox? Well, let's first wrap up here. We came up with this integer-based reformulation. And if we combine this integer-based reformulation with our first naive encryption approach, where we simply applied it on the real value data, then we end up with this encrypted controller here, right? So the idea was right, that with this encrypted additions and partially encrypted multiplications, we can realize it. However, we needed this integer-based realization to start with. Okay, for completeness, this here will be evaluated in the cloud. So the cloud computes the encrypted inputs. It then sends the result to the actuator, which does the decryption, the rescaling, and then applies the approximated input. And then next sampling instant, the sensor measures the current state, scales it, rounds it, encrypts it, and sends it back to the cloud. In order to apply this encrypted control scheme, we will use a simple benchmark system and the given feedback controller in the last line, and this is then implemented in our toolbox. By the way, our toolbox comes also with a tutorial paper. The tutorial paper is not yet in the proceedings for whatever reason, but there is an archive version with exactly the same title as this whole session. So if you Google it or whatever browser you're using, you will then find it. Okay, so how can we evaluate this encrypted controller using our toolbox? Well, first step, as I said, we need to tweak MATLAB a little bit because the default precision in MATLAB is far too low to handle these super large numbers with crypto systems. So we use this variable precision arithmetic, VPA, and there you can specify the number of digits. And with 100 digits, we are almost good most of the time, which makes everything slower, right? So if you increase the precision, then everything gets much slower. Then for this Payet example, you can use the Payet class. There's an operation key generator, and this will spit out the public and the secret key, and this can then be used later on to evaluate the encryptions and also to do the encoding. Now, we use the scaling of 1000, meaning we kind of preserve 3 digits, 3 decimals of our real-valued numbers. We map it to ZQ, where here again the Q is nothing else than the public key of the Payet scheme. And this functionality, the scaling and the modulo operation, this is all packed in the encoding function, because later on for the more complex crypto systems, also this encoding step. So getting our data ready for encryption will be much more complicated, and hence we kind of coupled everything together in this encoding routine. And here it's evaluated for the controller matrix, leading to this integer set k for a representation of the controller matrix. Now, if we implement the encrypted control loop, then at every time step we measure the current state. Well, we get it from our simulation. We apply the scaling, the modulo operation, the encoding, resulting in an integer z. Zx, we then encrypt it using this encryption routine with the public key, right? The public key is used for encryptions. And then here comes a nice feature. Then we evaluate this product, so k times x. That is what we are looking for in plain text. We learned that in the ciphertext space, it's much more complicated. We use this O plus and O dot operations. However, for convenience, we simply overloaded the multiplication operator, and hence you can write this as you would write in plain text, but under the hood, everything which we just mentioned happened using this homomorphic operations. Okay, and then we can apply it and run the simulation for our benchmark system. And well, the result is not too surprising. The benchmark system is stabilized. The dots here, they refer to the plaintext implementation. So every dot is a plaintext implementation, and then the lines, they refer to the encrypted realizations. And we see here different lines for different scaling parameters. So one very coarse one, and then we get finer and finer until we reach the 1000 that I was discussing on the slide before. And then you see that for this 1000, that is the dashed green line, we pick up all the dots from the plaintext values. So that is really a more or less one-to-one approximation of the plaintext realization. The state seems to be not so sensitive with respect to the inputs, meaning even for the most coarse implementation, we exactly pick up this state trajectory here. Okay, yeah, that's it for the first pioneering realization, but I will briefly prepare what is about to come in the next parts here. So woohoo, we implemented our first controller, that's cool. Question is it always that simple? Well, we neglected many things here. First of all, I just showed you the code, I haven't evaluated it, right? If you download our toolbox and evaluate it, you will find out it takes quite long, right? So there's a large computational overhead. As I said, there are much more efficient implementations, so do not worry too much about it. It's simply a bit annoying when running the code. But you can realize it faster, much faster, but still, there is a huge computational overhead with respect to the plaintext realizations. I mean, remember, we are computing u equals kx here, so there is no rocket science involved, but still, it takes quite long if we do it in an encrypted fashion. But we can get down to, well, I think milliseconds, tens of milliseconds, that would be realizable, but not with our MATLAB code. Okay, then, as I said initially, there is quite a weak motivation for putting u equals kx in the cloud if we are not talking about multi-agent systems. So we should look at more complex controllers where there's a benefit then of implementing them in an encrypted fashion. We won't do so within this tutorial session, but there are many works on encrypted MPC and stuff like that. So there are more complex controllers which can be realized in an encrypted fashion. Okay, and then, as I mentioned earlier, we only have a partial controller encryption here, right? So the controller parameters k, they are open, they are plain text and accessible, and maybe that is also something we worry about. Nicely, you can also realize the scheme if you say, I worry about my controller, but I don't worry about the privacy of my states. You can clearly interchange the role of k and x, right? So you can encrypt all the controller parameters using the Payet scheme and leave x open. But if you want to have both at the same time, then the Payet scheme can't offer that for you, and you need more complex control scheme, more complex crypto systems, and these crypto systems you will learn about in the next two parts. Okay, so meaning if we are looking for fully encryption of more complex schemes, then the challenge is quite hard quickly, and we then need this fully homomorphic encryption schemes, or at least the leveled versions of it. Leveled means that we have multiplications and additions, but only a finite time, right? The fully homomorphic scheme gives you additions and multiplications infinitely many, but here we often are dealing with leveled ones, so where you can have, whatever, 10 multiplications in a row or something like that. Details will follow in this regard. And another challenge which pops up frequently as in literature are control schemes involving iterations or recursions, right? That is kind of very hard for a crypto system if you keep adding up or multiplying things in an iterative fashion. And I will briefly mention on this problem because we will also pick this up in the upcoming talks. So, what is the prototype for analyzing these iterative schemes? In the literature, the prototype is kind of a linear dynamic controller of this form, which gets as an input the output of the system, has the controller state xz, and spits out the input for the system. Clearly, if we think about an integer-based reformulation here, we can use different scaling factors for the different parameters, but independent of how we realize it, we will end up with this issue that, I mean, similar to fixed point schemes, you need to make sure that if you add things, that they are at the same scaling level, right? And due to this issue, due to the iteration here, this iteration with the A matrix, that kind of accumulates the S1 scaling factor. And as a consequence, in time step k, we need to adapt the scaling of our system output y. And hence, we have this S1 to the power of k plus 1, which is an issue, because I said we have to make sure that no overflow happens. If we have this growing and growing scaling factor, then we will have an overflow almost for sure at some point. So that is an issue. Clearly, there is an easy way out. The easy way out is that the scaling factor S1 is simply set to 0. To 1, right? But then, I mean, here it's fine. We still have the scaling factor as 5, but it means that also here with the A matrix, we need to insert the 1, meaning for the integer-based realization, we just round our A matrix, the controller matrix, to the next best integer, and that is often an issue, right? It is no issue if your A matrix is an integer or almost an integer, then it would work. And many works also deal with this question. So can I realize controllers which having integer parameters? And that is also one point I would like to emphasize here, that these encrypted control stuff, it also initiates like interesting research questions and traditional system theory, because before there was no real reason to think about that. Why should I worry about integer controller parameters? But now it becomes an issue, and I can ask myself, what are the restrictions resulting from integer A? And they are quite heavy, as you might learn in these two papers here. One point where it's not heavy to have this restriction of an integer A is a PI controller. And a PI controller is a very simple realization of this dynamic controller. In fact, there, in this discrete time version, we would simply have the 1 here, and all the other parameters are also scalar here, sampling time, and then Ki and Kp. And if we then think about an integer-based realization of that, the following can be used. Again, make sure that the scaling kind of reflects what happens in the meantime and neglects all the scaling factors which were accumulated. And this is now a realization of the PI controller using integers, and this is ready for being encrypted. And in fact, we can also realize this in a partially encrypted fashion using Payet, but there we would have the controller parameters open. Later on, you will learn how this can be realized in a fully encrypted fashion. And here again, the simulation, same notation as before, and you see again that it works out nicely also using this control scheme. And that brings me to the end of of my part. Yeah, thanks for listening. So what are the two core messages here? Well, first of all, encrypted control is possible. We can realize controllers in an encrypted fashion. That is kind of the key message, using suitable tools like homomorphic encryption, for instance. But so far, we only saw very simple control schemes, and we also only saw partial encryptions. And now in the next two parts, we would like to look at more powerful crypto systems and also fully encrypted control schemes. However, we stay within this tutorial with the two examples, that is the dynamic controller in terms of the PI controller and the state feedback. Yeah, that's it for part one. Thanks for your attention. If you have any intermediate questions, feel free to ask, and then we will switch to the second part, given by Yunso.
Good afternoon. I'm Junsu Kim from Seoul National University of Science and Technology. Thanks to Murchi's introduction, we have covered the broader scope of issues in encrypted control and its necessity. And this time, I would like to be more focused on a specific type of encryption. And it's called LW-based crypto systems, and I would like to introduce how this scheme can be used for encrypted control and dynamic systems. So, as an introduction, I would like to begin with these three major interests. For example, homomorphic encryption can defend eavesdropping attacks, and it can prevent adversaries who hope to learn some information. But then still, preventing integrity attack is a current challenge. Although the encrypted messages conceals the value of the messages, but still an adversary may corrupt or compromise data. So in the future works, these future works are called in this way. Second, as Murchi has introduced, crypto systems usually support addition operation and multiplication operation. So that other than these two operations, still the other operations may be limited. So that, for example, ReLU operations for learning iterations, or sine, cosine functions, or the kind of comparison operation is still limited. So that implementing such operation is a major interest in encrypted control. This time, I would like to be focused on the third item. An issue is to enable recursive dynamic operation. For example, given two encrypted messages, if we want to perform multiplication only once, then by use of scale factors or other things, multiplication can be done. But when it comes to recursive dynamic operation, an encrypted number should be used for the multiplication again and again, then it leaves a challenge. So, regarding this problem, I would like to be elaborate on what the issue is. So, let's consider a dynamic controller here. Okay. So this time, let's consider a dynamic controller here, where X is the state, Y is the input, and U is the output. And here, I would like to call F is the state matrix of the controller. As you can see, as time goes by, running this dynamic system requires recursive multiplication at each sampling period. Given the state matrix should be multiplied so that it updates the next state, and then it should be reused for the multiplication at the next time step again and again. Then, I would say, given the state matrix as an integer matrix, once the state matrix is encrypted, the problem is twofold. In using current crypto system techniques, if the state matrix consists of non-integers, then currently I would say all encryption schemes allows for only finite time of multiplications only. It means that you can multiply on non-integer number or non-integer state matrix to the state, but the multiplication can be done only finite number of times. After a while, then it cannot continue the multiplication operation, so that, for example, refreshment techniques or bootstrapping techniques must be used. And furthermore, the second emphasizes that although the state matrix consists of only integers, still currently almost all crypto systems allows for multiplication only finite times. So in summary, if the state matrix is non-integers, then resolving this problem is almost impossible. And still, if the state matrix consists of only integers, still continuing the recursive operation is hard and restrictive. So this time, I would like to be focused on this problem and introduce the encryption scheme called LW and GSW. And this is the message of this talk. The scheme called GSW, which I would like to introduce this time. The benefit of this scheme is twofold, especially the multiplication method by GSW crypto system allows for multiplication infinite number of times if the state matrix consists of only integers. And it means that given a dynamic controller, as it naturally requires recursive multiplication every time steps, based on this benefit, I would like to deliver that GSW encryption is suitable for implementing linear dynamic operations. So far so good. So I would like to deliver the scheme details and related methods briefly, where I would like to follow the flow of the same flow of this tutorial paper as a reference. And again, this is the code-driven tutorial paper, so that I would like to dive into the code example to follow the details. And finally, let me conclude the talk with some additional notes. So, in the forthcoming 1 or 2 slides, it explains how we can encrypt a number. And I would like to deliver that it is very simple and intuitive so that you can keep this in mind and then you can encrypt something. So let's consider this space as the space of messages. The messages from 0 to the number q minus 1. So suppose that there's a fixed number between in this set. How would you conceal this information against an adversary? I would say one of the simplest methods to conceal this number is to sample a random number from this set and add this random number to the message and take the modulo operation with the number q. This operation means that you take the remainder divided by this number so that the outcome C1 is again one of the elements of this set. Then what would you expect? If we choose this number, random number R, from the uniform distribution of this set, which means that it has the same probability, 1 over q, from the element 0 to the element q minus 1. Then if we add this random number to the message and take the remainder, then you will this resulting probability variable will follow the same uniform distribution over this set. It means we can regard this number as an encryption. Given a message, we mask this message with some random number and take the remainder, so that the resulting with the resulting outcome, an adversary cannot find what the original message was, unless the adversary knows the value of the number R. So this encryption is somehow perfect in the sense that the adversary cannot learn anything, but then the recovery is still possible. The secret key is the information of the random number R, so that given the ciphertext, with this secret key, one can do the subtract operation and then obtain the real message. However, this is somehow nonsense and in terms of encryption, because whenever you do the encryption, you have to sample a random secret key all the time, and they are not compatible with the others. So in order for real encryption, we needed to generate a random-like number using a fixed secret key. So this is somehow the method for the encryption. This is not a toy example, and this is a real one. The method or intention is to generate a random-like number using a fixed secret key. So here, again, here's the message given. I would like to mask this message by adding some random-like number. The thing is, we first choose a secret key vector, which consists of n integers, and then we keep this in a secret vector. And what we do is to perform a dot product. This is the fixed secret key. And we sample n random numbers, which is denoted by from a sub 1 to a sub n. They are chosen as a uniform distribution numbers. And then we perform the dot product here and add some small error. The thing is, by doing so, it has been known that this portion of number, the fixed secret key multiplied by random numbers and plus some small error, it is known that this portion of number really looks like a random number, especially when the dimension of the vector increases as a parameter. Yeah, that's it. By doing this, you can encrypt any number. Given a message, choose a secret key. At the stage of encryption, you sample some random numbers and do the dot product and add some small number. Indeed, in terms of security, it is known that it is secure. One knows the secret key, he or she can learn the message from the ciphertext. Otherwise, from an adversary's point of view, without knowledge of the secret key, it has been known that the adversary cannot never learn the message, the value of the message or the value of the secret key. So technically, it is called learning with errors problem. So given a measurement or given a bunch of encrypted numbers, which are encrypted with the same secret key, the problem is to solve this system of linear equation over the space C sub q, and then learn the information of the unknown variable secret key. But it is really known that, given this information of ciphertext and the random numbers, solving this equation and learning the information of secret key is hard. And moreover, given the set of ciphertext, given the set of encrypted numbers, it is known that figuring out if these encrypted numbers are just random numbers or some generated number using the secret key is also hard. So it means that if you encrypt any numbers using this scheme, from the adversary's point of view, it cannot be distinguished from a random sample or this encrypted message sample. It means that it is secure. And moreover, this encryption is homomorphic. So based on this security, you can encrypt any given number by this scheme. Given an integer here, yeah, that's it. Given an integer here, you just add a random-like number and then take the modulo operation. Then you also have this vector A as a public information. Then that's it. This is the encryption. The thing to remember is that the encrypted message consists of 3 parts. Here, the M is the message part, and the masking part, colored red, is called the random-like term, and here is a small error added. So whenever you encrypt a number, then it consists of these 3 parts. And decryption itself is quite simple. It is nothing but canceling out the red term only. The decryption is to multiply a row vector, including a secret key from the left, then you can imagine the situation. By multiplying this row vector from the left, given an encrypted number, you can expect that this row vector multiplied by this red column vector, they will be cancelled out. So that once the red part cancelled out, you will have only the message part and the error part. So that you can recover the original message with some small error. Here, you can remember that once you encrypt a scalar number, then you will obtain a vector whose dimension is n, which is n plus 1. So this is because when you encrypt this number, then the resulting vector was in this form, where the first component was containing the message part, and the other part is the random vector part, whose dimension is n. You may be concerned about the small error, but it can be eliminated by use of scale vector. First of all, the error is assumed to be sampled from uniform samples from Gaussian distribution, so that in practice you may assume the error is bounded by certain multiple of the standard deviation. Then, by choosing a scale factor, which is sufficiently large compared to the standard deviation, then when you multiply the message m, you simply first multiply the scale factor and then encrypt them. And what enough follows, we can recover the exact message, not corrupted by the errors. This is because when you decrypt the scaled message, you will obtain the message scaled by the number L plus a small error. But we have assumed that this number L is sufficiently large, so that when we divide the number L again, then we have this term where we can assume that this second term is sufficiently small. Because then, by taking the rounding operation, we can obtain the original message without effect of error. So far, so good. Now we can encrypt the message, and we can decrypt the message. And the method itself is very simple. And here, benefit is that it is homomorphic. Once encrypted, they can be used for operations such as addition and constant multiplication. And later, I will also elaborate on about the multiplication. This is because the underlying idea is that the decryption method or decryption algorithm was nothing but multiplying this row vector from the left, which is basically a linear operation, right? So that you can expect that given any two ciphertexts, when you add them together, you can imagine that the message part will be added together, so that when you try to decrypt the operation outcome of the addition, then by the simple distributive law, multiplying this secret key of the outcome of the addition is equal to addition of the decrypted messages of 2. Again, it is also homomorphic with respect to integer multiplication as well, because again, the decryption operation is linear, so that when you multiply this number k, the message part will be multiplied k times, so that when you decrypt it, you will obtain the message part, decryption outcome multiplied by k times. So far, so good. So doing the addition is quite simple, as simple as the encryption algorithm. But the following question is, how can we multiply a ciphertext with a ciphertext? You remember, once we encrypt a scalar value, it turns into a vector, an n-dimensional vector. So that the question is this: here, given two ciphertexts, C1 is also a vector, C2 is also a vector. How would you do the multiplication between the two ciphertexts? Regarding the linearity, you may think that there is no natural way to multiply these two vectors. So the following idea is, what if we can encrypt one of these two ciphertexts as a square matrix? Then we can imagine that if C1 were a square matrix, then it can be multiplied with the column vector C2, and this will result in, again, an n-dimensional vector. So that's it. In order for multiplication, we slightly modify the encryption method so that encryption of one number results in a square matrix. Then it allows for the multiplication operation. So I would like to denote, the notation is a little bit different from the first talk, but I would like to denote the second encryption method by inc prime, which maps a scalar message to a square matrix. But still, it is based on the same encryption method and the same encryption problem. Again, after the encryption, the ciphertext consists of three parts again. It consists of the message part, random-like part, and the error part, where we apply LW-based encryption column-wisely. We have seen in the previous slide that this column, this first column added by this small error column results in a random-like number, right? So that we simply generate n columns of ciphertext, so that from the first to the nth encrypted number, we list this column of ciphertext column-wisely, so that it results in n by n ciphertext. So we added this random-like matrix, and we generate this small random-like small error matrix, and add them all together, and keep the message part as an identity matrix multiplied by the message k. Then, given a scalar message, after the encryption, we have the n by n matrix, which can be multiplied with a vector of LW type ciphertext. Indeed, this was C1 in the previous slide, and this is C2 in the previous slide. Now we have one of them kept as a square matrix. We can multiply with each of them. Then, after the multiplication, we obtain n-dimensional vector, which is the form of the LW type encryption. Indeed, this operation is also linear, so that when you decrypt this number, the decryption was to multiply the row vector of the secret key from the left. Then after some calculation, you can see, again, the red part is canceled out, and you obtain the message part plus some errors. But here, there is some sophisticated issue, which is the error is multiplied by some number. C was the encrypt message, so that it consists of large numbers, so that there is the sophisticated issue. It is homomorphic and it is linear, but after the decryption, you obtain the message part added by arbitrarily large number. So that this was not the real GSW method. So we need some modification regarding this error growth. So I would like to a little bit skip the detail, but the thing is, which change the method of multiplication. For example, regarding this multiplication, 7 multiplied by 11 is 77, but there is another method for the multiplication. When we express this number 11 using the binary system, then we can express number using binary numbers. Then we can, by use of associative law, we can express the multiplication process in a slightly different way. But by this idea, you can see that the right term, which is the multiplicand, consists of far smaller numbers. So it can be generalized so that given k and given x, the multiplication can be done in a different way by use of this kind of binary decomposition or generalized decomposition, where the multiplicand is decomposed into far smaller numbers. Yeah. So by this idea, the issue can be solved. So I would skip this part, but the idea is the same. Given the message, after the encryption, it again consists of the message part, random-like part, and error part. But in order to introduce the different method for the multiplication, there is some modification. But after this, you can see when it comes to multiplication, the multiplicand on the right term consists of far smaller numbers because of decomposition. So after this part, when you check the homomorphic property, now the issue is resolved. Again, the multiplication is linear, so that after the decretion, you obtain the random-like part cancelled out, and you have only the message part and the error part. But this time, you will see the small error is multiplied by only small numbers. So this error growth you can deal with, so that in this manner, the multiplication done over ciphertext. So at last, we obtain this property of multiplication. It means that you can see, given any ciphertext, C is a vector, n-dimensional vector, column vector, which was the LW type encryption. Whatever you have a scalar number as a multiplier, you can do the multiplication. You can encrypt this number, and you take the decomposition for the multiplicand, and then multiply them. And when you decrypt them, then you will obtain the message part multiplied with each other plus small error. This is the property of GSW, which allows for both addition and multiplication. So multiplication by scalars is implementable, and also matrix vector multiplication is implementable because it is nothing but consecutive operation of addition and multiplication. By component-wise encryption, you can encrypt a matrix using the GSW method, and given an LW type ciphertext, you can do the matrix multiplication in the same way. Because of time, I would like to skip this part, but what I want to deliver was the message. The message was this. There are several types of encryption. At this time, I am introducing the GSW encryption scheme. Its benefit is that it allows for multiplication of integer unlimited number of times. It can be seen, this property can be seen in this equation. So this is the same equation where x was an LW type ciphertext, and here inc prime denotes the GSW multiplication. The thing is, the ciphertext x can be any ciphertext. So when you do the ciphertext multiplication, the LW type multiplication is LW type ciphertext is multiplied by a matrix encrypted message, and it results in the LW type ciphertext, so that it can be reused for the operation, so that it can be reused for the multiplication operation again and again, because this property ensures that the homomorphic property holds for any LW type ciphertext, which could be a newly encrypted one, or the or the ciphertext which has been used for multiplication several times. So this is the result. Based on this property, it ensures that multiplication by an encrypted number is applicable for infinite number of times, so that as we have seen in the formulation page, such kind of operation is essential for the linear time systems, so that it means that continuing linear dynamic operation on ciphertext is possible if the controller is multiplying the state matrix consists of integers, so that it can be encrypted as in this form with GSW encryption. This is a little bit technical proposition, but it is still saying that recursive multiplication by an integer matrix is possible, and regarding its performance, it is equivalent to systems over real numbers. So we can think of this system where X is the encrypted state and F is the state matrix. The ciphertext X is kept as an LW type encryption, so that it can be used for the GSW type encryption, so that it can be first decomposed and then multiplied by the GSW type encryption. Then it results in an LW type ciphertext, so that it can be used again and again for the encrypted multiplication, so that running this dynamic system over encrypted data is possible. And then after decrypt this state for the analysis, then you can find its performance is exactly the same with that of the linear systems, with the presence of small errors because of the use of encryption. But as we have seen, by use of scale factor, we have seen that the size of the error is bounded, and we can choose the scale factor arbitrarily large, so that this perturbation term or error term can be made arbitrarily small. Which means, by choice of parameters, the performance of the encrypted system is equivalent to that of the real system, consists of the real state vector and the state matrix. So this is the message. Based on this method, linear systems having state matrix consisting of integers is implementable over encrypted data, where both the state matrix and the state can be encrypted. That's it. That's all for the technical part, and some brief remark is following. One good part, or the major benefit of GSW is that it can allow for recursive multiplication, and a minor, and in addition to that, a minor strong point is that it allows for a simple structure and easy implementation as well. In contrast to failure encryption, where in failure encryption, when you hope to perform the addition operation, then in practice you have to implement multiplication between big integers. In contrast to that, if you use the GSW encryption, then the operation structure is the same. If you want to implement addition operation, then you can just perform addition operation between two ciphertexts. And if you wanted to perform multiplication operation, then aside from the decomposition operation, what you actually do for the encrypted multiplication is to perform large size matrix and vector multiplication. However, there is weaknesses as well. The weaknesses of GSW scheme is that encryption of a scalar message results in a large size matrix. We have seen that for the LW type encryption, when you encrypt a scalar, it results in n-dimensional vector. But then when it comes to GSW multiplication, when you encrypt a number, then it results in a square matrix whose dimension is n square. In practice, it means that in practice, because of security, the parameters, the crypto system parameters are often required to be larger and larger. For example, the dimension n is chosen 1,000 or 2,000, this kind of scale because of security. But depending on this security level, the dimension of the matrix increases increases quadratically with the scale n square. However, this issue will be resolved in the forthcoming talk. Actually, this GSW multiplication is nothing but a basic method for the tutorial, and it is easier to understand and implement. But this scheme has been introduced in 2013. It has been already 10 years, so that this issue of large-sized matrix has been resolved so that it can be elaborated on in the next talk. This session was the code-driven session, so that I would like to go into the details with the codes and implementation examples. Again, here is the QR code so that you can download the simple live MATLAB codes, so that, and then you can run and test how it works. I guess the size of the font is a little bit small, but it just follows that follows the same flow of the technical details of this talk. The first thing is LW encryption, so that you can by the MATLAB code you can see how it really encrypts a number using the LW type encryption. Here I am testing with the message 0.2. And then I have chosen the scale factor as 10,000, so that after the scaling, the message is turned into an integer, so that I can encrypt this number using LW type encryption. It results in an n-dimensional vector, where the parameter n is chosen as 4, so that n plus 1 is equal to 5. Once you encrypt a message, scalar message, then it results in 5-dimensional vector. Indeed, you can access to the encrypted data. What you will find is this small message turned into 5-dimensional vector consisting of large numbers. Based on the LW problem, without the knowledge of secret key from the adversarial side, learning the information of message or the secret key is difficult. And we have seen the LW type encryption is linear, so that it is homomorphic with respect to simple addition operations, so that we can directly check that property. Once you add a ciphertext by a ciphertext, both of them were containing the message 0.2, and then when you decrypt the operation outcome, then you will obtain the operational outcome that matches to the plain text operation, which is 0.2 added by 0.2, which is equal to 0.4. But here there is a slight effect of the message, but we have seen this effect of error can be eliminated by use of scale factors. Similarly, public multiplication is also possible, so that you can check this simple property as well. And the benefit of GSW was recursive multiplication, so that this code can also confirm that benefit as well. So what we have seen is once you encrypt a number using the GSW multiplication, it results in a matrix with a large dimension. You can see that situation here. Here, the value of the message is 0.4, and I am encrypting this number using the GSW encryption with the code, and you can see it results in this size of matrix. In this example, n was equal to 4, so that n plus 1 is equal to 5. And here, the decomposition parameter is chosen as 20, so that after the encryption, a scalar variable turns into a matrix having 100 rows and 5 columns, so that it results in this large size matrix consisting of large numbers, which is encrypted. So that you can check the property of multiplication as well, so that when you do the multiplication and decrypt it, you will obtain the operation outcome matches to the operation outcome that matches to the plain text. And then you can also check that this multiplication method can be used for control example. Regarding the encrypted state feedback, where multiplication of ciphertext and no ciphertext is used, so that it considers the state feedback controller consisting of the matrix multiplication, but it is implementable. And in terms of performance, although all of them are encrypted and operation is performed, their performance is equivalent to that of the plain text controllers. And the emphasis was that GSW multiplication can be applied recursively infinite many times. You can check this property as well. Here, given a dynamic controller, it is a PI controller, so that there is an integrator for the state part, which means that the state matrix is the identity matrix, but they are consist of integers, so that you can encrypt this state matrix using the GSW encryption. And then you can multiply this encrypted matrix to the encrypted state again and again for an infinite number of times. Despite the recursive operation, still the performance is equivalent, and so that it is sufficient to stabilize the plant. Time has run out, so that I would like to conclude this talk. Still, I want to emphasize that this was the tutorial session, but still, in terms of the research problems and challenges, I really believe that the field of encrypted control is still young. So combining the control theory and the cryptographic primitives, new problems are still found again and again, so that there are much things to do. So I should finish here, and thank you for your attention.
Well, thank you, and yeah, let me begin with the last part. I'm going to introduce the CKKS crypto system. So CKKS is one of the state-of-the-art crypto systems in this context. And I think Junso already gave some motivation. But before we start, I want to give you a brief overview about all these different crypto systems, because there are quite a lot. So what Moritz was already telling us is about partial homomorphic encryption. So the Perrier scheme is one of the examples there. It's already 30 years old. And then we have some breakthrough papers by Regev and Gentry. And from these emerged basically two branches. So we have two of these branches. In one of them, we have the GSW scheme that Junso told us about. And in the other one, we have the CKKS scheme, which is the content of this talk. And the upper branch is known for fast bootstrapping. We will later see what that actually means. But really, the takeaway message there is you can operate only on small integers. That is due to the scheme characteristics. Whereas in the lower branch, this is where you want to go if you want to do arithmetic, which is usually the case when we implement control algorithms. So slight difference in notation. I will use centered representatives for my finite set. So it goes from minus q half until q half, the integers in that set. And the modulo operation is then defined as follows. We have here a modulo q is a minus q, and then we have not the flooring, but the rounding operation, rounding to the nearest integer. And because of that, a generalized fixed point encoding that is also, has also been introduced in Moritz's talk, in the first talk, is then by applying the scaling factor s to a real number x, rounding it to the nearest number, applying the modulo q operation. And because we have these centered representatives, we do not need this modulo inverse function we can simply decode by dividing with the appropriate scale factor. So this is because the sign is preserved in this centered representatives. All right. And I think Junso already gave us some motivation for using other crypto systems. Here I just wanted to briefly mention the complexity of the LWE cipher. So Junso already introduced this with this left arrow I denote sampling from a set or from a distribution. So the LWE problem was sample A from this finite set, sample your secret key from a distribution, sample your error from a distribution, and then construct these LWE instances. And the LWE problem is then find the secret key. And this is the problem that gives the hardness in order to construct crypto systems on top of that. And if we encrypt a message vector of size z, then already Junso told us that we get a vector of encryptions, and we can see if we simply stack these LWE instances on top of each other and put our message inside, so z is the message here, then we can see that we get a large matrix out of it. And this matrix, if we assume that the number of messages is a large n, then comes with a time and space complexity of n squared. And how can we improve on that? Well, cryptography came up with algebraic abstraction. So before we had computations in the ring of integers in this ZQ, where we had addition and multiplication defined. We have now computations in ring of polynomials. So this is our polynomial ring. We have polynomials in terms of a large x. And these polynomials come with coefficients that are inside the set ZQ. And then afterwards, they're reduced with this irreducible polynomial. And what this actually means is basically you have elements that are these polynomials a of x. They have an order that is limited by n-1, so you never have a polynomial with a larger order than that. And the coefficients are from this finite set ZQ. The coefficients are denoted with a tilde. And what we can then define on this set, as it's stated, it's a ring. We have the addition and the multiplication operation. The addition is very easy. We have component-wise addition of the coefficients, whereas the multiplication is slightly more complex. As you can imagine, you have two polynomials, you multiply them, then this is also commonly known as a convolution. In this case, due to this modulo reduction and reduction by this polynomial x to the power of n+1, it's actually a negative wrapped convolution, and it works as follows. First, you multiply both of these elements. Then you divide by this x to the power of n+1. You take the remainder, so this is a polynomial division. You take the remainder of that. And then you reduce every coefficient by mod q. And in fact, this gives us the nice property that we can apply something that is related to a Fourier transformation, which is called number theoretic transformation in this context. And this enables us to multiply these two polynomials a of x and b of x in n log n time. So really there's a speed up in computations due to that. And it works as follows. We apply this number theoretic transformation to both of these polynomials. We have then a component-wise multiplication. We apply the inverse transformation, and then we get the result we wanted inside our polynomial set. If we then want to construct a crypto system on top of that, we have not the LWE problem, but the ring LWE problem. So everything is now based on polynomial rings. A is now sampled from this polynomial ring. And the secret key is also from a polynomial ring distribution as well as the error. And then we construct our LWE instance. It looks exactly the same as before, but only with polynomials now. And for clarity or for brevity, I will drop the of x in the following. So everything that you see here is a polynomial, but we do not explicitly make the of x notation in the following. And if we encrypt the message then, we take the message from the set RQ. It has n coefficients now because the polynomial has this many coefficients. And we can encrypt it as we did before. But now our dimension is not as high. So our space complexity is now n, because we have 2 times n coefficients, and our space time complexity is mainly due to the multiplication. It's n log n. So we get really an improvement in efficiency due to that. And this is really the reason why we want to use this weird ring abstraction. Right, and why do I tell you about this? The reason for that is because basically every homomorphic crypto system that is efficient or is state-of-the-art, uses this ring construction. And the Keon Kim Song CKKS crypto system is one of them. I will first tell you about computations in CKKS. I hope to give you a broad overview where you can maybe find some guidelines. Then we have plain text encoding. How do we encode our messages in these polynomials? We talk about some basic functionality. With that I mean decryption, encryption, and also we will talk about the homomorphisms, which is really what we care about in order to implement encrypted control. Finally, some additional features, if we have time for that, the control examples, and then we will end with a short summary and outlook. So how does computation in CKKS look like? First, we encrypt the ciphertext. We encrypt the plain text in a ciphertext. I denote this here by the CT. And in CKKS, the ciphertexts come with a specific modulus that may change over time. So we have this modulus Q with with an index L at the very beginning. And this really comes from encoding our vector X inside the polynomial, and then we encrypt the polynomial. So we have a mapping from the set of complex numbers in this case. The reason, you can also use real numbers, of course, because it's a subset from it. It's the encoding that is defined in this in this context in order to realize the encryption with certain properties. We get our polynomial rings, and then we encrypt from the polynomial rings to the polynomial rings with the square here. The first ciphertext, as I said, comes with a modulus. The modulus is QL, which consists of a base modulus Q0, a scaling factor S, and this is raised to the power L, where L is the multiplicative depth or level. Moritz already mentioned that we have a certain level in CKKS, and this is really one of the core concepts. Because if we do computations on certain ciphertexts by using the homomorphic addition and multiplication, then after each multiplication, one level is consumed, so the level reduces over time. This is also shown here. So at some point, we might have a level of QL, where this L is from the set 1 until L minus 1. So for example, if you have the homomorphic multiplication, then at the end, you will have a ciphertext that has a reduced level. And that is also the reason why we call this leveled fully homomorphic encryption. Right. When we reach the base modulus, Q0, the ciphertext must be decrypted in order to ensure correctness. So after that, you can, in principle, compute further, but there's no guarantee that the result will be correct. So what we do then is we apply the decryption function and the decoding function denoted here. And your job as a control engineer would then, in this context, be represent a given computation, a given algorithm in terms of these homomorphisms, and to pick a suitable amount of levels L. And to give you an example how this might look like, consider, for example, the computation Z1 times Z2 squared. You can write this also in two different forms. The first one would be like this, with these brackets, and the second one like this. And the concept of levels then boils down to these computation graphs, where you can see that in the first graph we have a depth of the graph being 2, so the height of this graph is really what defines the level, the number of successive multiplication. And on the right-hand side, because we poorly designed our circuit, we have a depth of 3. So the level is bigger in this case because we need 3 successive multiplications. The height of the graph is larger, and this also increases our modulus, which then in turn decreases the efficiency of our crypto system. All right. So that is basically the overview. Let's start with the plaintext encoding. So very naive encoding would be take coefficients of a vector x, put them inside the coefficients of the polynomial. So in this case, we have here that z tilde is the same as the component of our vector xi. And then we apply then suppose we apply the homomorphic operations on that. That works fine with the addition because, as we said before, the addition is component-wise. But with a multiplication, it's a convolution. And the convolution of Z1 times Z2 is rarely an operation that we want to implement with encrypted controllers. So what we could do in that context is restrict ourselves to a scalar encoding, where we only use one of the coefficients of our polynomial. So we only put one of the elements inside there, which is of course a waste because we have n coefficients and we only use one of that. So what would be desired is an encoding where we can use more coefficients, something where the decoding of Z1 plus Z2 is the component-wise addition of our vectors, and the decoding of Z1 times Z2 is the decoding of the component-wise multiplication. That is something we would like to have, because then we can really make use of the coefficients. And the intuition here is that we basically can apply something like an inverse DFT-like transformation, because this inverse DFT-like transformation then really maps the convolution to these component-wise multiplications. It's actually defined here. Do not worry so much about how it actually works. It's basically the same idea as in Fourier transformations. The matrix may look a little bit different. We have some roots of unity as well. The core concept is basically the same. What we have also here is the scaling factor S. So this is still used. And we basically apply our matrices, the bar is the conjugation, by the way, to the vectors we have. We scale it, and then we round the result as usual. So that is mapping our vector x to integers, z tilde, and these integers are then put inside the coefficients of the polynomials. And this is then what gives us the opportunity to compute on the components in the polynomial. For the decoding, we simply reverse the mapping by using the inverse of the matrix, which happens to be the conjugate, and then we divide by the appropriate scaling factor. And due to the specific construction of this mapping, we can then use n-half of the coefficients in our polynomial. So this allows us to use SIMD, or single instruction multiple data operations, on n-half of the coefficients, which allows us to batch computations, which makes it more efficient. So in our toolbox, we can see how this is realized. On the left-hand side here, we have a look at the scalar case first. We have a scaling factor. We have n equal 4. Here are two numbers, 1 and 2, which are our plain text that are first encoded into our message. Here's Z1 is the message polynomial. And the polynomials are internally realized by the properties using coefficients, a scaling factor, a modulus, and a type. The type is, in this case, the scalar. And we can see that this, then the output of this is then 1,000, because only one of the coefficients is used. There we have the encoded value. For the second one, it's then 2,000 because of the scaling factor 10 to the power 3. And if we add that, we get, of course, 3,000. If we decode it, we get 3 because the scaling factor was 1,000 during the computations. If we have the ring multiplication here, the scaling factor grows, as Moritz already told us, because the multiplication increases the scaling factor. And therefore, we need to decode with the appropriate scaling factor. This is done internally by using the scaling property of the polynomials. And then, of course, we get here the result, which is 2. So 1 times 2 is 2. In the packed case, it works very similar. The difference here is we can use multiple values. We have 1 and minus 2 in here, and 3 and 4 in the second plain text vector. These are then encoded. We can see that the polynomials now look a bit different. But then if we decode our values, we get 4 and 2 as expected, because 1 plus 3 is 4 and minus 2 plus 4 is 2. And for the multiplication, we get here 3 and minus 8, so component-wise multiplication, which is what we desired. The basic functionality, so decryption and encryption, are realized by first setting up the crypto system. Don't worry too much about the details here. It's just important that there are some ways in order to ensure a certain security for a given computational depth, L, which is set by the user. And then we have a key generation where we basically generate our secret key and a public key. And with that at hand, we can use, again, an LWE instance where we embed our message. It looks a bit different here because it's a public key scheme. If you just rearrange it a bit, you will see that you end up with an LWE instance right here. So basically, this public key encryption gives you the very similar structure as before, but it looks a bit different. But do not worry about it too much now. The decryption, as Yunsu has also shown us, is basically by picking from the encryption tuple the A vector, multiplying it by the secret key, and adding it to the B inside the tuple. And what we get then is Z plus some small error. So the message plus some small error. And in CKKS, the error is usually considered to be part of the message, which is a characteristic of CKKS. Right. In the toolbox, it looks like this. Let's not go in too much detail. I just want you to know that the ciphertext has some more properties. In fact, it is represented by one of these polynomial ring elements in the first tuple, ring element in the second tuple. It has a certain level, it has a scaling factor, and the toolbox is really taking care of everything regarding the computations for you. The interesting part here is, of course, the homomorphisms. The first one is pretty easy. So the additive homomorphism is basically literally adding the ciphertext. So you take the B of the first ciphertext of the second, you add them, and for the second element of the tuple, you do that as well. And it's literally that easy because the encryption is linear. For the multiplication, it's a little bit more complicated, and it's different compared to GSW. So in GSW, you had this bit decomposition that is used in order to realize the multiplication. And here, it looks a bit different. We have first this tuple here, which contains D0 and D1, and we have some additional term that is shown here. And really what the idea is, let me quickly go over this. Really what the idea is, when you look at two numbers that are decrypted inside two ciphertexts, so the decryption of the first one is given here and the decryption of the second one is given here, then this is really the result you desire, Z1 times Z2. If you just multiply out the decryptions here, you will see that you will end up with something that is with D0, D1, and D2 that is defined as above inside the multiplication routine here. So really, we want to construct the multiplication in this way because this gives us our desired results at 1 times Z2. But what comes out of here is, of course, something that is containing the secret key in a squared fashion. And we do not want that in a squared fashion because if we keep on multiplying, the squared goes to the 4th power, to the 8th power, and so on. So this is really not maintainable if you have multiple multiplications. So this is where the second part of this multiplication routine comes into play. So this one here, which is basically if you decrypt it, decrypting to D2 plus SK squared plus D2 times something extra, where P is a really big number that is constructed in the key generation phase such that this additional term is small. And this gives you really the extra term, and it gets rid of the extra term this gives you the extra term in this SK squared fashion that you need in order to have the correct decryption, while not explicitly having it in here in the ciphertext. In the toolbox, we have a small example to evaluate a polynomial because now we can evaluate a little bit more complex functions, not only linear functions. We have here the polynomial arbitrarily chosen by x to the power of 4, y squared, x minus y plus y. And we can see that in the toolbox here, we have a ciphertext for x. We generate a ciphertext for y. Then we simply evaluate the polynomial. The toolbox takes care of the addition, multiplication, and also the squaring for you. And if we decrypt it, we can see that we get the result polynomial, where we have used the scalar encoding. So only one of these coefficients is relevant for us. And the relevant coefficient is of course the last one here with 62.17. The correct result with floating point arithmetic would be 62.65. So there's also a small error that we introduce by the encryption. Quick side note, you can of course reduce the error as much as you want by increasing the scaling factor. Then also we have additional features in CKKS. These are rescale. Rescale is really an important part of CKKS because it gives you the opportunity to divide your plain text your message by a scaling factor and then round it to the nearest result. And it really, when you multiply it and you have the scaling factor increase, as Moritz already showed us, then you want to bring the scaling factor down in order to have this, to avoid the scaling factor increase and to run into an overflow. But this comes actually at a cost. By reducing the scaling factor here, we also reduce the modulus. And this is really how the levels arise in CKKS. So the rescaling operation reduces the modulus, and that is why we have this leveled kind of scheme where the modulus reduces. Because rescale is executed after every multiplication. The reason for that is, so you might wonder, why would you do that? Of course, we have a scaling factor decrease, but also we decrease the modulus in this way by the same amount. So why would that be helpful? Well, the reason for that is if we reduce the scaling factor and keep it linear, instead of letting it grow quadratically and to the fourth power and so on, then it grows actually exponentially, as you can see. Whereas if we do the rescaling after every operation, the modulus is actually reduced by a linear amount. So if we execute the rescaling after every multiplication, we get exponentially more multiplications that we can perform with our scheme. This comes at the cost that we have to have a common modulus between two ciphertexts in order to have a useful operation between them. And you can always apply the rescale operation or do a modulus reduction in order to achieve that. Two additional features that are defined in CKKS are key switch and rotation. I will not go into detail here. Just briefly, I wanted to just briefly mention that key switching is a nice feature if you want to do multi-party computation, because you can switch from a scheme that is or a ciphertext that is encrypted under one secret key. You can switch it to a ciphertext that is encrypted under another secret key, so they can be interchanged between different parties, and they can compute on that. And rotation is useful if you want to rotate the slots into in the plain text. This is especially required for linear algebra in these schemes. Then there's one advanced feature which is called bootstrapping. Bootstrapping, as Moritz told us, is this special operation that basically gives us an unlimited amount of operations. We have this leveled CKKS scheme. When we reach the base modulus, we have to decrypt. That is what we saw on the previous slides. But bootstrapping is really the operation that gives us an unlimited amount of operations. Basically, this works by increasing the modulus, the base modulus of our ciphertext, to a larger modulus Q, and that is in CKKS done as follows. We simply interpret the ciphertext that is at the base modulus in this large modulus, and then there comes a different term into play, which is a multiple of our base modulus that would usually be reduced if we simply apply our modulo Q0 reduction. But in this case, of course, because we have defined now a larger modulus, the larger modulus does not affect the smaller term. So we need to get rid of it. And in CKKS, bootstrapping is really a homomorphic way to eliminate this extra term, this additional term that would be reduced by modulo Q0 reduction. Of course, you can try to implement a modulo Q reduction in a homomorphic fashion, but this is often very inefficient. What is done in literature usually is we assume that the message is very small in compared to our base modulus, and then we use a sign approximation of the modulo function. So basically, the orange curve is the sign, and the green curve is the modulo. And in this small region around 0 here, where our message may be, so, we have linearity, and therefore both in the modulo reduction and also in the sign. And this is really what we want for a message, because we do not want to alter the message, but we get rid of the modulo reduction because we have, but we get rid of the additional Q0 term in here, because we basically approximate the modulo reduction. Yeah, that's about what I wanted to say about bootstrapping, just to give you a brief idea. And let's now finally dive into the remaining control examples. So here we have the plain text state feedback. This is the MATLAB implementation of that. Yunsu and also Moritz already told you about the convergence properties. The encrypted state feedback in CKKS looks very similar. It's a little bit different. We have here the encoding. We have the encryption of K and X. Again, everything is overloaded. So here we have the computation of the control input, we have the decoding, and we apply it to our linear system dynamic, encode at our sensor again, encrypt at our sensor again, and then evaluate again our state feedback on another device. In this context, we assume it's a cloud. Right. For the PI control, it behaves very similarly. We have the encrypted implementation in a very similar fashion. Here, of course, we need to not only encrypt the states, but also as before. Oh, 1 second. In this example, of course, we do not only encrypt the states, but also the feedback gains. And of course, we do that also for the PI control case, because the CKKS crypto system really allows us to encrypt the whole computation. So this is really what I wanted to deliver for the control examples. And let me briefly summarize this talk. We have seen at the very beginning an extension of LWE to ring LWE, which gives us the efficiency and the reduced time complexity and space complexity, which is required in order to achieve better runtimes. CKKS essentially allows you to compute on SIMD evaluation of multivariate polynomials. So in every slot of your ciphertext, you can evaluate multivariate polynomials, and that is what you have to work with. And the research opportunity then in the context of control is you are a specialist in control, you know how the algorithms work, and you can now go ahead and reformulate your algorithms such that they are really compatible with these schemes. The other thing is bootstrapping becomes necessary for large or unknown depth computation. That is and bootstrapping is really inefficient operation because the sign approximation that is usually used requires a lot of computation. And the research opportunity here is to find optimizations suitable for control. One of these optimizations is to have an integer formulation of your controller, as Moritz suggested and also Yunsu suggested, and come up with different schemes that work well in this context. Of course, the computational burden is still an issue. If we reflect on what I've just said, it's basically we do all of these computations, these algebraic abstractions, and at the end we simply get addition and multiplication. And you will also see in the examples of the MATLAB toolbox that, as Moritz already said, it's not particularly fast. So we also have to work on the computational burden in order to reduce the running times and to get it to a practical level. Right. So with that, I want to conclude and end my talk. Thank you for the kind attention, and I'm very happy to answer your questions if you have any questions. In which form?
Can you implement a Leuenberger observer?
A linear dynamic observer?
Yes.
As we've already seen, it depends on your state matrix. Of course, you can do anything with homomorphic encryption. The promise is multiplication and addition gives you everything you need. But if you have these infinite iterations that are required for the observer, in the normal fashion, like the linear system iterations, at some point you will need to implement bootstrapping. So you will get a large delay in your computations at that point when you execute the bootstrapping routine. Otherwise, you will have to come up with something like an integer formulation of your observer, which then gives you the opportunity to compute indefinitely on the data, because you don't have this accumulation of the scaling factors.
Thank you.
You're welcome.
So I'm curious about the computational efficiency. So you mentioned that there
Yeah.
are faster implementations, but just to get an idea of where we are, if you have a 2x2 system.
So don't want to say something wrong. The variable precision arithmetic toolbox in MATLAB is quite slow from my point of view. The runtimes for like the plain text PI controller or something is in CKKS for 20 iterations, like half a minute or something like that. I haven't had measurement for every operation. First of all, MATLAB is quite slow in that regard. My implementation is not really, or our implementation is not really optimized for speed. It's like for educational purposes. You can get down to milliseconds for a single multiplication, or even a little bit below that at the current state. Addition is quite fast in that compared to multiplications. But you will probably, if you want to do really a fast implementation, you should use like the maintained toolboxes available for that in C++. It's OpenFHE, or in Rust there's also some implementation for a scheme that I haven't mentioned here. But that will give you a better running time for sure.
Thank you very much.